Hi, today in this video we are going to see how we can use the CST Studio Suite software for designing microstrip lines. Basically, microstrip lines are used for the transmission of RF signals from point A to point B on PCBs, that is the printed circuit boards. Either you are working on designing of the antenna radiators or working on circuits, that is the microwave circuits, for example power amplifier, low noise amplifier, oscillators, and other circuits that are actually generating or transmitting or amplifying RF signals. So these microstrip lines are required there for the transmission of RF signal from point A to point B, and it is critical to have good impedance matching from point A to point B and minimum standing waves to ensure efficient transmission of the signal and low noise. Let's start the project by first going to the project template and then selecting the microwave and RF optical antennas. Click next, click on the planar patch, next, select the time domain option, next, and keep the default units, or you can change any of the unit you desire. And then for now we are going to select frequency from 0 to 40 gigahertz so that we can just generalize this tutorial and see how the microstrip transmission line will act for low frequency as well as for high frequencies, right? So click next and finally click finish. Within a moment you will see that the project is ready. So first things first, press Ctrl S and save it, this tutorial, anywhere you want, right? So for example, I want to file this or name this tutorial as tutorial 1, right? And click save, because most of the time uh, this human error occurs that you are working on a project and you forget to save the project, and due to some software glitch the CST Studio software stopped working. So all the work that you had done previously will be lost, right? So this is very important. Now what we are going to do is we are going to design a simple transmission line on a PCB. But before going to the design phase, we have to calculate the width of the transmission line, as that width will decide the impedance, right? So for that we are on this home tab, click on macros, calculate, and select the calculate analytical line impedance. Here you will see the calculator for different types of transmission lines, for example coaxial, strip line, thick strip line. Today we are working on the thin microstrip lines, right? So the image is demonstrating that this width is going to be uh, tested here to see for what value of width we are going to get the impedance, right? The line impedance. So also we are going to set the height of the substrate, and it is critical to know that this height do not include the height of the ground strip, right? That is under this substrate. So say for example we are selecting the frequency 1 gigahertz, but I will show you that this frequency do not have much effect on this impedance, right? So for this tutorial we are going to work on the FR4 substrate, as it is cheap and easily readily available. So you can easily check and download the data sheet of the FR4 substrate, and you will know that the most common value of the height of that substrate is 1.6 millimeters, right? So we're going to set 1.6 millimeter height, and the relative permittivity, uh, it's 4.3. You can check the values of it on the data sheet. The substrate permittivity may vary, so I'm just setting a generic value that is quite famous, right? So we have set the frequency to 1 gigahertz, the height to 1.6 gigahertz, the relative permittivity to 4.3, and now what we are going to do is click on calculate, and here we can see the impedance of this transmission line is 64 ohms for a width of 2, right? So what we can do is change the width to 3 and check it, right? You can see that the impedance is now very close to 50 ohms. Since most of the RF circuits has a standard impedance of 50 ohms, and that is why we are going to set the impedance to 50 ohms here as well. So if I set it to 3.1, so it will be 50 ohms, right? So we are going to select this value and we are going to copy it. Also, before closing this calculator, I would like to show you that if we set the frequency to 40 gigahertz, so you can see the impedance, there is no change in the impedance, right? But the only shift is in the phase shift, right? So impedance is do not have any changes while we are changing the frequency, or if we change the height of the substrate, then definitely this impedance will change. So you have to carefully select the value of the height and the relative permittivity of the substrate you are working on, right? So now we have the value of the width of the transmission line for 50 ohm impedance. Simply copy it in the memory and go to modeling and select this brick. Click here and press the escape button. Now you can see that we have the option to set the name of the uh, brick as well as the its dimensions, right? So first things first, we are going to set or design the ground uh, of that PCB. So as it is since it is the below most of the layers, right? So for that we can name it to G and D, and for now we are going to set the length in x-axis as -10 to 10 mm, the width in the y direction from -10 to 10 mm. This is kind of random values, but you can change these values for your desired application. Right now we just want to design a simple strip line to check the impedance and its performance, right? So the Z, that is the thickness, will be set to from 0 to 0.035, that is 35 micrometers, as most of the copper thickness on these substrate comes with 35 micrometer. Also we are going to select the material from material library, and we are going to type copper, and we are going to select the copper annealed, as this comes with the lossy metal option, right? But if you select the pure copper, so such copper is available in the market. Uh, like this is the lossless kind of lossless, so it is better to select the copper annealed, right? Select it and click load, and you can preview it. Right here you can see the ground, the design of the ground, and on the number pad simply press 1 2 3 4 5 to change the orientation uh, from where you want to see the strip line. That is a microstrip that we are designing. For now we are going to finalize it and click OK. And as you can see, we have the ground patch ready. We can also disable the working plane as well as the boundary box, so that we can have a better look on this ground patch, right? So step 1 is complete, and we can see that this is from minus 10 to 10 mm, minus to 10 mm, and 0 to 0.035 mm or 35 micrometers. Step 2 will be designing of the substrate. So we are going to repeat the process and name this as substrate. Again we are going to set it from minus 10 to 10 mm, minus 10 to 10 mm, and the Z. Now the Z will be selected as, since we know that this point is 0 and this is 0.035, right? So I'm going to set 0.035, and maximum should be 1.6. Now if you look carefully, uh, if we set this value to 0, then the design substrate will be exact 1.6 mm in thickness, right? But since we are moving in the upward direction, in the Z direction, 0.035 or 35 micrometers, so we have to add this value as well on this portion, right? So that we should get the exact 1.6 mm thickness in the Z direction, right? And now for the material, we are again going to select the substrate material, which is FR4 from the material library, and we are going to select the lossy to get the as much realistic results as possible. We can click on preview to preview it, right? And finally we can click on the OK. And as you can see, we have the substrate ready, and we can also check the dimensions, that is 0.035. Here the value is rounded off to 0.04. So also we can see the thickness of this substrate, so it's 1.6 mm, right? Now what we need to do is we are going to design the thin microstrip right at the center of the substrate in the Y direction, right? The length should be in the Y direction. You can set the length in the X direction as well, so it's totally up to you. I mostly set the width in the X direction and length in the Y direction, but you can set it as per your desire. Again we are going to select the break option. Here we are going to write the name as line. The X is the thickness, so we calculated it. Now we are going to paste that value here, and we are going to keep it equally right from the center So it should be 3.1 divided by 2 and 3.1 divided by 2, which means it will be 3.1 divided by 2 from the center towards the left side and 3.1 divided by 2 towards the right side. So the total width of that strip line will be exactly 3.1 millimeters, right? The length will be from minus 10 to 10 mm. And now for the height, we are going to see that this is 0, this is 0.035, right? So first we are going to go from 0 to 0.035. Now we are at this position, and if you want to go here, we have to add 1.6. Right now we are at this point, so simply copy this, paste it here, and again add 0.035. Now this value will be the height of the microstrip line, right? So we can click on preview, and as you can see here, the strip line is designed right at top of the substrate and its midpoint. Also, select the material to copper annealed, click preview, and finally click OK. So here we can see that the strip line is ready. Its length is 20 mm in total, and the width is 3.1 mm. We can ensure it by checking it. As you can see, it's 3.1 mm, and dimensions towards is the y direction, it's 20 mm, right? So we can, for now, we can delete the dimensions right from here. Simply click on the dimension and press the delete button. Alright, so our microstrip line, that is the microstrip transmission line, is ready to be tested. And now we are going to select the faces of the transmission line by pressing the F button here and double click on this face. As you can see, now it is highlighted and selected. Go to simulation tab, press the waveguide port, and now the values in the X direction and in the Z direction, right? So the thumb rule is that we should set it as 3 times the width of the transmission line. Again, in the positive direction, it will be 3 times width of transmission line. For the Z minimum, it will be 1.6, which is the height of substrate, and plus 0.035, which is the thickness of the ground, and finally in the Z positive direction, it will be 4 times the height of the substrate, which is 1.6 mm, right? So as you can see, this will be the port, that is the waveguide port. Simply press OK, and we can see the port is designed, and you can also ensure that the port is actually touching this ground as well, right? Alright, so port 1 is has been designed. Now it's time for the design of port 2. Repeat the process by pressing F button, selecting the face, clicking on waveguide port, and set the values for this port as well. Now you can see that the transmission line is design is completed. We have attached the waveguide ports to it, and finally we are going to start the simulation. We can click on this setup solver now, and you can see the time domain solver parameters here are can be changed. Mesh type is hexahedral, and accuracy is minus 40 dB. So for better accuracy we can go up to minus 50, 60 and 80, or for less accuracy we can reduce it to minus 20. So I'll keep it as the default option, which is minus 40, and we are going to start the simulation. Here we can see that the simulation has been started, and now it will take a while to complete. Since we have set the frequency from 0 to 40 gigahertz, so definitely for this range of frequency it will take a while to complete, right? But the positive side is that we can actually see how well this transmission line will transfer the RF signal from point A or port A towards the port B or port 2, and for which frequencies the losses will be minimum, and for which frequencies the losses will get higher, right? So this is the uh, advantage of designing such type of transmission lines first, before actually designing your circuit, to see and ensure that this the designed transmission line or the planned transmission line is the has the right width to ensure good transmission, right? And there should be minimum standing waves while the RF signal is being transmitted. So now I'm going to stop the video here, and we are going to see when this simulation gets completed, right? Alright, so the simulation has been completed successfully, and now we are going to see the results of this transmission line, that how well this transmission line is capable of transmission of signal from port A towards the port B for different frequencies from 0 to 40 gigahertz, right? So for that, what we are going to do is simply click on the 1D results and go to S parameter results by pressing this plus sign, and here you can see that we have four different results here, that is S11, S12, S21, S12 and S22. So the thumb rule for reading this S11 is actually, or what it actually means is that the signal uh, gets transmitted from this port 1, that is this one, and it is moving towards port 2, but due to standing waves it gets back reflected towards the port 1, so it will be like in anti-clockwise direction, right? Similarly for this S21 is the signal gets transmitted from port 1 towards the port 2, right? So this will show you the S21, that is transmission of signal from port 1 to port 2. S12 means that the signal gets transmitted from port 2, right, from here towards the port 1, right? And finally S22 means that signal was transmitted from port 2, but due to standing waves or the reflections the signal gets back towards the port 2. So first we are going to see S12, that is or S21, that is the transmission of signal from port 1 towards the port 2. Here you can see this is the graph from 0 to 40 gigahertz. The signal, the standard signal that this CST software generates is 0 dB, right? So that means that 0 dB power of signal was generated and transmitted from port 1, and it get received at port 2. So as you can see here that for lower frequencies, that is from 5 gigahertz to nearly 10 gigahertz, the line is linear, right? So as you can see that if I set it right here, and these two lines at this point, so we can see that we get a bandwidth of nearly 4 gigahertz, for which the transmission of the signal from port A to port B is quite linear, and it is the value is -1, means -1 dB of losses occurred for this frequency range, right? Or when we can also add a curve marker at any point we want, like this. Simply right click on add curve marker, and double click on any location you want to add the curve marker, and after setting it, simply press escape to get out from that curve marker settings, right? So you can move that marker anywhere you want, and you can see that for 40 gigahertz the losses of for the transmission of signal from port A to port B is -3.8 dBm, right? So this is the transmission from port E or port 1 to port 2, and this graph shows the transmission of signal from port 2 towards the port 1, right? So this is also similar, since the this transmission line has symmetry, so obviously it will show similar results for S21 as well as for S12. um, Here we can see that for lower frequencies, specifically for 5 to 10 gigahertz, we have the minimum losses for the transmission of signals, and S11 and S22 shows that the reflections or the standing waves that occurred, as you can see here for lower frequencies, we can see that the reflections are quite low, but for higher frequency the reflections are quite high, right? The reason for this multi depths is because for higher frequencies, such type of transmission line starts to radiate, uh, although it will not have good efficiency and gain, but it will still radiate. That is why we are looking at these dips, right? So these dips are showing kind of radiations, since the standing waves are quite minimum right here. Okay, so one more thing that we are going to see here, that for example, if we want to tune or optimize this transmission line for uh, getting the best length of this transmission line in terms of results, right? The width was calculated using the line calculator, but what about the length? So usually we set it as lambda by 4, but if we want to now tune this length of this transmission line, so the problem here is we have not set the parameters right while designing of these strip line and the ground and the substrate. So what we can do here is we can start with the ground, and it is a good practice to always set parameters uh, at the start of your design, so that it can easily be tuned during the design, right? So since we know that we want to change the length in the y direction, uh, so in the positive y direction, right? So we are going to go to the ground, and in the y maximum, instead of setting the value directly here, we are going to give it a variable name. So for example, I set the variable name here as a, right? So, or you can set it, they give it proper name as ground underscore length, right? Copy this variable name, uh, and it will ask you the value. So we are going to set it to 10, which is the current value. Also we need to set the same parameter for the transmission line, since the value has been set here, so it will not ask you again. Also for the substrate, set the same parameter, right? So now the parameter ground length has been set to 10 millimeters, and it is quite easy now to change the value of this parameter. And as you can see, while I'm changing it, uh, the ground, the substrate, and the microstrip length is changing at the same time, and it is quite easy to set the length, right? uh, One more pro or the advantage of setting the parameter here is we can actually now tune this parameter for different values by selecting the option parameter sweep, and we are going to set new sequence, new parameter. Since we have only one parameter here, that is the ground length, it will show you only that option. And we are going to set it line linear sweep, and from value should be from 5 to say 15, right? And you can either set the number of samples here, or you can set the step width. Say I'm setting it to 5. So here you can see that for that 5 step width, it is going to test for the length 5 millimeter, 10 millimeter, and 15 millimeter. So a total of 3 iterations, right? We can check this by clicking on check, and it is going to show you that uh, it will go through 3 iterations. And finally we can click on this start button to start the simulation. Now this simulation will take a bit of time, because it is going to first simulate it for length of 5 millimeter, and then for 10 millimeter, and then for 15 millimeter. So we can actually compare the results at the end of simulation, that for which value of length we are getting better results, right? So after that we can easily select that specific value for the best results, right? So again, I'm going to stop this video, and we are going to see the results after completion of this simulation. Alright, so the simulation has been completed now, and we can actually check the results of that parameter sweep. We are going to check the S parameter for S21, that is signal transmission from port 1 to port 2, right? So as you can see, we have 3 different graphs here. The red graph shows the length of the transmission line for 5 mm. The green line shows the result for length of transmission line for 10 mm, and the blue one shows for 15 mm. Uh, Previously we set the length to 10 mm, and as you can see here, the value 15 mm presents more losses for higher frequencies, right? While the 5 mm length, the losses are lower for this 5 mm length of the transmission line. So the purpose of this parameter sweep was just to show you how you can uh, use the parameter sweep option in order to uh, check different values whenever you are working on any project, right? So you can set the parameter sweep to a specific range, and after that you can see which value is going to give you the best result. And finally we can set that value. For example, here in this case it is 5 mm. So what we are going to do is we are going towards the parameter sweep and we are going to set the value to 5 mm, right? And then we press the F7 button, and you can see the length is now set to 5 mm, right? Also we can one more option that I want to show you is if you go into post processing, we can actually delete all the results that are saved in the cache by pressing this button, delete results, and all the results that were saved in the cache will be deleted, right? So I hope you understood the concept of designing the transmission line for RF circuits. Either you are planning to work on design of antenna radiators, or if you are going to design microwave circuits. So this tutorial is going to help you, right? So that's all for today. If you have any queries related to this tutorial, you can simply ask me in the comment section. For now, take care, have fun, bye bye.